The reaction of hydroiodic acid with ethers is specific in two aspects. One is I minus is a weak base. Now Hi is a strong acid, so there will be a greater concentration of H positive. Means I minus will be having a lesser tendency to combine with H positive to give undissociated acid. And again the bond energy is very low, that is why Hi is more acidic. That is one reason. And again another reason is that I minus is a weak base, so it will be having a lesser tendency to combine with the H positive to give back the acid. So that since I minus is a weak base, elimination reaction is less favored by I minus. Now iodide ion is a large ion, so it is highly polarizable. Means its electron cloud can be easily distorted by a positive carbon. So this also favors the nucleophilic reaction over elimination reaction. So two important reasons, that is I minus is a weak base, so elimination is prevented, and I minus is a good nucleophile because it is highly polarizable. Hence it acts as a good nucleophile. Now the dissociation of ethers by hydroiodic acid can occur by either SN2 mechanism or SN1 mechanism. Now if the alkyl loops are primary alkyl loops, then the SN2 mechanism operates. Now the less hindered alpha carbon is attacked by the nucleophile, that is I negative. Now consider the case of methoxyethane. It is also called ethyl methyl ether. Now here there are two alpha carbons, two types of alpha carbons. One is alpha dash and the other is alpha. Now the less sterically hindered, in the sense the alpha position which is having lower number of bulky groups. Here this methyl is a bulky group. So approach of I negative from this side is sterically prevented. There is steric repulsion between the approaching I negative and this methyl group, whereas here we are having only small groups, that is hydrogen atoms. So I minus can easily attack from this side than this side. So alpha carbon is being attacked by the iodide ion. Initial step of reaction with the hydroiodic acid is the protonation of oxygen. Oxygen using one of its lone pair will bond to H positive from Hi. So I minus is made free. That is a fast reaction because, and again reversible because either is not a good base. So this oxonium ion will remove H as H positive and will give back this ether molecule. So this is a fast reversible reaction. Now I minus formed will react with this ion, oxonium ion, at the less hindered point, that is the methyl carbon. This is an SN2 reaction because this is the slow step, and in the slow step I minus attack the less sterically hindrance means opposition, sterically hindered carbon, and we get a weak bond between iodine and alpha carbon. and the bond between C and O is partially broken, so that oxygen atom, positive oxygen being highly electronegative, will be pulling this pair of electron towards itself. I minus is trying to establish a bond with this alpha carbon. So in the transition state TS, there will be partial bond between I negative and oxygen. Withdrawing this electron pair gradually neutralizes its charge, so that the positive one charge here changes to delta positive, and since the lone pair of iodine is partially forming bond with the alpha carbon, the negative charge of iodine is getting lowered to delta negative, and we get an SN2 transition state. Now, as soon as the transition state is formed, it will easily establish strong bond between iodine and carbon, the usual covalent bond, and this bond completely breaks, so that the positive charge, delta positive charge over oxygen is neutralized, and the delta negative charge over iodine is neutralized. Because when this bond is completely removed, carbon bears a positive charge which is neutralized by the negative charge of iodine, and we get ICH3 and CH3CH2OH. Now another example. Now let us look at the alpha carbons in this example. Now both these carbons are primary carbons, so there is no chance for SN1 reaction, there is only chance for SN2 reaction. Now there are two alpha positions, alpha and alpha dash, because this alpha carbon is connected to a very bulky group. This as a whole is acting as a bulky group. So that SN2 reaction occurs by attack by the nucleophile iodine at the less hindered alpha carbon, that is CH2 carbon. So break this bond, HI acts like this, we get CH3CH2I and CH2OH. Now both these are primary carbons, but this is more sterically hindered carbon, so attack by I negative at this carbon is opposed by the steric repulsion of this bulky group, whereas here we are having a small, comparatively small methyl group. So preferential attack over this alpha dash carbon, so we can easily predict which product will be formed, that is I minus will be connected to this portion and H will be connected to this portion. So the products CH3, CH2I and CH2OH, this one alcohol. Now the molecule, this may be called the derivative of 1, 2, 3, parent is propane, and this is also a propyl group, so it is called a propoxy propane. Propoxy, PRO POXY, propoxy propane. Now both the alkyl groups are propyl groups, so both these alpha carbons are having similar environment, so that we say they are equivalent, they are similarly placed. So HI can act here or here, you will get the same product in both cases. Now this OCH2 bond breaks, and I minus connects to this carbon and H connects to this carbon. Or better, we can break this bond, I minus going over to this carbon and H positive going over to oxygen, which is more electronegative. It's an SN2 reaction because it is a primary carbon. So first oxonium ion is formed, then I minus attacks this carbon, establishes a weak bond, and this bond is getting broken, and we get OH here and CH2I here. So the products are propanol and propyl iodide. Now write the mechanism of reaction of HI with methoxymethane. Symbol, first of all, H positive connects to oxygen, forming OH bond with a positive charge over oxygen. That's a fast reversible reaction because either is not a good base. So reversible reaction occurs, and then I minus can attack this carbon or this carbon, both are equally placed or similarly placed, equivalent methyl groups, and we get this transition state which completes the reaction by complete shift of this pair of this negative charge in between iodine and oxygen, so that this bond becomes a full bond. Similarly, this bond is a partial bond, it completely breaks, and this delta positive charge is completely neutralized. We get methyl iodide and methanol, very simple. Now, assignment mechanism occurs when one of the alkyl groups is a tertiary alkyl group where the tertiary carbon is directly bonded to oxygen of either group. Now here this tertiary carbon is directly bonded to oxygen, so there can be the chance of formation of this tertiary butyl carbocation. First of all, H positive connects to oxygen using oxygen's lone pair, we get OH positive. Now this bond can shift in this direction, giving a carbocation and methanol. So this is a fast reaction because it is reversible and easy addition of H positive to oxygen atom. The second step is SN1 reaction, and that is a slow step because it involves breakage of a bond. So it is slow and reversible. We get methanol and tertiary butyl carbocation. It is reversible because this methanol molecule, oxygen containing a lone pair, can undergo nucleophilic reaction with this positive carbon, producing back the protonated derivative. So it is reversible. Now this carbocation will be attacked by I minus, which is a good nucleophile, and this positive carbon can easily polarize the large anion. The iodide ion being large in size, highly polarizable, the positive carbon polarizes iodide easily, so iodide is a good nucleophile, and the reaction is fast because it is bond formation, and bond formation is exothermic and spontaneous. So that is assignment reaction. Now there is another example for assignment reaction given by this molecule. We know this carbocation will be formed because it is tertiary. So H positive will connect to this oxygen, so we get CH3, CH2, CH2, OH. And iodine will be getting connected to this carbon, so this bond will be getting broken. So we can predict the product formed. Now coming to aromatic ethers, the specialty with the preparation of aromatic ethers is that aryl halides, means halogen connected to benzene ring. Now there is a mesomeric effect of halogen, so that electron density is injected into the benzene ring, and the carbon to halogen bond attains double bond character, so breakage of this bond is easy. So that is due to mesomeric effect or resonance effect. So we cannot prepare aromatic ethers from aromatic halogen compounds. So aliphatic halogen compounds are selected, and then phenol being acidic, with sodium hydroxide it can give sodium salt of phenol, and Na and I can get removed as sodium iodide, and CH3 connects to O. So removal of NaI, and you get OCH3. This molecule is called anisole or methoxybenzene. Now there is another compound where the alkyl group is ethyl group. It is called phenetol or ethoxybenzene. You take sodium phenoxide and ethyl iodides. Now methoxy group is electron donating, means shows plus some effect. There is a weak minus I effect also. Now plus some effect is important, so that electron density accumulates in the ortho and para positions. Shift of electron pair, bond formation, valency of this carbon rises. This pi 1 ionizes like this, so the valency of carbon is maintained 4. Then we get negative charge, shift of this lone pair of electron, or we can start from the arrow negative, from the negative sign we can start the arrow. Now this arrow showing this pi electron pair gathering into the orbital of the carbon here and negative charge. So resonance can occur, making the ortho and para positions electron rich. Now one difference between phenol and this molecule anisole is that phenol can form phenolate anion. Now the phenolate anion is more stable because there is only one negative charge, whereas in free phenol, in the canonical structures, we have positive and negative charges. Greater the number of charges, higher will be the instability because of the interaction between charges. Now in a phenolate anion, there is only one charge, so there is no charge interaction, and the phenolate anion is stabilized more. And again, more stabilization of the molecule means more contribution of canonical structures, and the contribution of canonical structures where the ortho and para positions are electron rich is slightly higher than the canonical structures of corresponding phenolic structures. We infer that the phenolate anion contain a higher electron density in the ortho and para position, and this is why phenol molecule undergoes active electrophilic substitution, because free phenol in water also ionizes as phenolate anion and H positive, so that bromine water will react with bromine water will react with the anion of phenol, because the electron density of ortho and para positions are much higher than that in the ortho and para positions of free phenol. Here this molecule, either molecule, cannot ionize to give the phenolate anion, so the ethers are less reactive than phenols, and the OR group is said to be ortho para directing, in the sense during electrophilic substitution an electrophile, for example nitronium ion or methyl cation or acetyl cation or a bromine cation, will enter into ortho and para positions, and there again the ortho position is hindered, sterically opposed by the methyl group, so that much amount of para product is formed than the ortho product. Then bromination using bromine in acetic acid. So milder conditions are only needed for bromination. We get parabromomethoxybenzene or parabromoanisole. And orthobromoanisole are formed, parabromoanisole being formed to the extent of 90%. And for alkylation, we use Friedel-Crafts reaction, that is alkyl halide and anhydrous aluminum chloride. The electrophile is alkyl carbocation, so that here the electrophile is CH3 positive. This ionizes Cl negative and combines with AlCl3 forming AlCl4 negative, because aluminum can provide a vacant orbital. It's a Lewis acid, so that Cl negative can coordinate with the vacant orbital of aluminum, and this ion pair containing methyl cation will be acting as the electrophile, and we get the major product as the para product, paramethyl anisole and orthomethyl anisole, ortho being less in amount due to steric repulsion between the methyl groups. Now acetylation reaction is also comes under the heading of Friedel-Crafts reaction. We use anhydrous aluminum chloride and acetyl chloride CH3COCl. Then COCH3 group is connected at the ortho and para positions. We get para derivative. Then it is considered as a derivative of acetophenone. So paramethoxy acetophenone, it's a ketone. So the parent compound is a ketone here. Or a keto group is given preference to either group. So C double bond O gets preference over either. So it is paramethoxy acetophenone. This ONE indicates ketonic group. So we get a mixture of the para and ortho derivative. Again, ortho derivative is found to be lesser in amount due to steric repulsion between this methyl and this methyl, and this CO group also. Now nitration can occur in para-nitro derivative is formed in excess amount due to repulsion between methyl and nitro group. A mixture of acids, concentrated sulfuric acid and concentrated nitric acid may be used. We get para-nitroanisole and ortho-nitroanisole, para-nitroanisole being the prominent products. Now action of hydroiodic acid on aromatic ethers. Now here, due to resonance or mesomeric effect, the CO bond here is strengthened, in the sense it acquires double bond character, so it is difficult to break this bond. So the only choice is breakage of this bond. So when this bond is broken, we should get CS positive and OS negative. So C positive will get connected to I negative and OH. But the mechanism is SN2, in the sense H positive first connects to this oxygen, giving the oxonium ion. It is ion 1 marked here. So it is an oxonium ion. Oxonium means positive charges over oxygen. Now resonance involving lone pair of oxygen here is not possible, but this bond is short due to the fact that the carbon here is sp2 hybridized and it forms a shorter bond and a stronger bond, whereas this carbon is sp3 hybridized and it forms a longer bond and hence a weaker bond. So here bond strength is higher. Resonance chance is less in this case because one lone pair is there over oxygen atom, because one pair is given to coordination with the H positive. There is a remaining pair, but that pair of electron will not enter into resonance because then the oxygen atom will carry positive 2 charge. That is not possible, or such a canonical structure is highly unstable. But again, this bond is stronger. So naturally there is a chance for breakage of this bond, and since this carbocation cannot be free, iodide attacks at this carbon by an SN2 mechanism, which is slow process. We get phenol and CH3I. So this is an SN2 mechanism. Now another example for SN1 mechanism. SN1 mechanism of course. So previously we have discussed the SN2 mechanism. So one example for SN1 mechanism, that is benzyl phenyl ether, we can call it. This is a benzyl group, BENZYL, benzyl, PHENYL, benzyl phenyl ether. Or it may be called benzyl oxybenzene. Anyway, this bond will be strengthened due to resonance, we can say, but proton when acts, this bond cannot be strengthened by resonance. But this is an sp2 carbon and oxygen overlaps with an sp2 carbon. The sp2 hybrid orbitals are shorter in length, so shorter bond is formed, and a shorter the bond, stronger is the bond. So naturally there is a chance for a shift of this pair of electron in this direction. And why this mechanism is SN1? Because when this pair of electron shifts over the oxygen atom, in the sense, and this pair of electron is taken up entirely by the orbital of oxygen, it neutralizes its charge and charge is formed over this carbon. Carbon gets a positive charge and this cation is called benzyl cation. Now phenol is one product. This benzyl cation is stabilized by resonance. So such canonical structures may be drawn. And this benzyl cation will be attacked easily by iodide the nucleophile in a fast step, and we get benzyl iodide. So that's enough. Thank you.